Good evening, everyone.
Good evening, everyone. Good evening, everyone. Good evening.
I hope I'm audible. Can you please let me know if I'm audible?
कर दिया मतलब अपलोड कर
Yes, you are audible, ma'am.
Okay. So, my name is Nidhi. I'll be taking your tutorial for this course on real analysis. So, mainly we'll be discussing the exercise problems that were meant to be solved by you. I'll be helping you for solving that. So, I hope you all must have gone through the video lectures, theory classes for last 1 week. So let's start with some problems related to matrix spaces. So this is tutorial one, question number one. So let's do one problem on matrix space. We'll be proving that this is a matrix space. Let X be the space R2 for any X, which is a tuple in R2, and Y again a tuple in R2. We define dxy equals to mod x1 minus y1 whenever x2 is equal to y2, and this is equal to mod x1 plus mod y1 plus mod x2 minus y2 whenever x2 is not equal to y2. So check whether this D forms a matrix on the space R2 or not. Check whether XD is a matrix space or not. I would like you to try this first. So start with the basic four properties that we need to in order to prove that a function is a matrix. So I'll just recall them. So if D, which is defined from x cross x to R plus, satisfies the following. Number one, dxy is sorry dxx is positive for every x in x. Dxx is 0 if and only if x is equal to 0. The third one is the symmetry. Dxy is equal to dyx for every x, y, and x. And fourth one is the triangles inequality. Xy is less than equal to dxz plus dzy for every x, y, z, and x. Please try to see whether this function D is satisfying the conditions of a matrix or not. I'll wait for a few minutes. You try and please let me know if you're able to prove it, whether this is a matrix or not. So I hope you are well aware of the definition and all. No? If you have any doubt, please ask me. Yes. Yes, Mayank.
Hello, ma'am.
Yes.
I have a doubt.
Hmm.
When we were doing the classes,
Hmm.
sir has defined metric space in terms under three conditions.
Yeah,
And here,
he must have said these two in one, na? I've just made
yes,
them two different conditions. That's it.
oh, okay. But I guess third one and he combined the third one and the second one. Sorry, third one and the fourth one.
How can these two be combined? So, anyways, these four conditions were there, na?
Yeah, indirectly, yeah, we can
Indirectly.
say.
I've just split them so that you can see in more details.
Okay, ma'am. Thank you.
Okay, so let me do this. Was anyone able to prove whether this is a metric space or not? Okay, fine, I'll do. So, firstly, we need to show that this is positive. This one is I have written wrong. This dxy is positive, dxy is 0, and only if x is equal. So let's start with the positive part. Clearly, since in the definition we have modulus, so everything is positive. Clearly, now dxy, this is mod x1 minus y1, positive. In the second case also, all the terms are positive. This is sum of positive terms. So eventually this is all positive. Okay. Next, we need to show that this is 0 if and only if both x and y are equal. Let dxy is equal to 0. Now, since x and y are arbitrary elements in R2, there are possibility then that x2 is equal to y2 or x2 is not equal to y2. Or x is equal to x1, x2, and y is equal to y1, y2, both belonging to R2. So let's start with the first case. If x2 is equal to y2, in that case, we know that dxy is defined to be equal to mod x1 minus y1. Now this is equal to 0 implies mod x1 minus y1 is equal to 0. Obviously, when modulus of something is 0, that means that something is 0. That means x1 minus y1 is 0. It is x1 is equal to y1. We already had x2 is equal to y2. We got this first component equal as well. That means x1, x2 is equal to y1, y2. Or we can say x is equal to y. Next case 2, when x2 is not equal to y2. In this case, we have 0 is equal to dxy, and by definition, this dxy is equal to mod x1 plus mod y1 plus mod x2 minus y2. So basically, we want to show if this is a this forms a matrix. In that case, we should have dxy is equal to 0 if and only if x is equal to y. Now, if this case happens, that means that x cannot be equal to y. So eventually, we need to show that somehow this case is impossible. So I mean, this case is absurd, something like that. So let's see. This is saying now these three are three positive terms, three positive numbers. Their sum is equal to 0. That means all of them are equal to 0, because if sum of positive terms is 0, that means all the terms are 0. From here, we are getting x2 minus y2 is equal to 0, x2 is equal to y2. But we started with x2 not equal to y2. Therefore, we get a contradiction. And hence, this case does not exist. Therefore, dxy equal to 0 implies x is equal to y. Conversely, clearly you can see that if x is equal to y, in that case, obviously x2 will be equal to y2, and dxy will be equal to mod x1 minus y1. And since x is equal to y, so x1 is also equal to y1. This is equal to 0. Therefore, dxy is 0 if and only if x is equal to y. Therefore, the second condition holds. Now, next, third, the symmetry condition. This is again very trivial. X1 plus y1, when x2 is equal to y2, this is equal to mod x1 x2 minus y2 when x2 is not equal to y2. Since everywhere we have modulus, we can write it like this as well. Just using commutativity of real numbers and the property of modulus. Now this is equal to d by x. This case was rather trivial. The next main important is the triangles inequality. Let's see how we can prove that. Let x, y, z belonging to R2 be arbitrary. We need to show that dxy is less than equal to dxz plus dzy. So let's start with x and y. For xy, we again have two possibilities. Either x2 is equal to y2 or x2 is not equal to y2. Let's start with case 1 when x2 is equal to y2. In this case, our dxy, this is equal to mod x1 minus y1. Now, while looking at now we need to introduce this element z and also. So for that we will again have two possibilities. So I'll write it as subcase 1 when z2 is also equal to x2 equals to y2, and subcase 2 will be when, I'll write it as z2 is not equal to x2, which is equal to y2. So we have these two subcategories. So in this case, we have dxz. So dxz, since x2 is equal to z2, this will be equal to mod x1 minus z1 dzy. This will be mod y1 minus z1. So this implies dxy, which is mod x1 minus y1. I can simply add and subtract z1 in between and then use the triangles inequality of modulus. And from here we get this is equal to dxz plus dzy. Therefore, this holds for this case. Similarly, we'll look for other cases. So here, in this case, dxz, now x2 is not equal to z2. In this case, we have dxz is equal to mod x1 plus mod z1 plus mod x1 x2 minus z2, and dyz, or I should where that doesn't make difference, dzy, this is equal to mod z1 plus mod y1 plus mod z2 minus y2. So this implies dxz plus dzy. This is equal to mod x1 plus mod y1 plus 2 times mod z1 mod x2 minus z2 plus mod z2 minus y2. Now again we'll be using this triangles inequality property of modulus. Z2 minus y2. This is greater than equal to mod x1 plus mod y1 plus 2 times mod z1 plus mod x2 minus y2. Because again, the way we do mod x2 minus y2 and then we introduce plus minus z2 in between, and then by triangles inequality we have something like this, z2 minus y2. So this term is greater than equal to mod z2 minus y2. That's what I've used here. Now this is again, anyways, this was not read. Okay, this is greater than equal to mod x1 plus mod y1 plus 2 times mod z1, because this modulus is obviously greater than equal to 0, and it can be written as mod y1 plus mod z1, which is again greater than equal to mod x1 minus z1 plus mod z1 minus y1. Again using triangles inequality. And this is again using triangles inequality. This is greater than equal to mod x1 minus y1, which is dxy. Yeah, because x2 was equal to y2, that's how we had dxy. Yes. So eventually in both the cases, we got the triangles inequality dxy less than equal to dxz plus dzy. Next comes the case when x2 is not equal to y2. There also, in that case, we will have three subcases. So it will be better if you write it all yourself and see how these cases, subcases are dealt to not equal to y2. In this case, dxy, this is equal to mod x1 plus mod y1 plus mod x2 minus y2. Here we will have three subcases. So the first subcase would be when neither of them are equal. That means x2 not equal to y2, not equal to z2. And this is not again not equal to x2, y. So neither of them are equal. In this case, we have dxy, this is equal to mod x1 plus mod y1 plus mod x2 minus y2, which can be written as less than equal to mod x1 plus mod y1. I'll introduce 2 times mod z1 so that we get terms related to z1. And since mod z1 is positive, this will not affect. And again, here also I'll introduce z2 plus z2 and minus z2. So again, by triangles inequality, this is mod x1 plus z1. From here, we'll get mod x2 minus z2. It's mod y1 plus mod z1. And from this part, we'll get mod z2 minus y2, which is now since x1 is not equal to z1, and since x2 is not equal to z2, so dxz is equal to this dxz. And again, since y2 is not equal to z2, dzy is equal to this term. So we get the required inequality. So I hope this case was clear. Then we'll move to next case when x2 is not equal to y2 and x2 is not equal to y2, but z2 is equal to y2. Okay. Subcase 2. In fact, subcase 2 and 3 are same. I'll leave 3 for you and show how this case is done. X2 is not equal to y2, but this is equal to z2. So in this case, dxz, this is equal to, since x2 is not equal to z2, so this is plus z1 plus x2 minus z2 and dzy, since z2 is equal to y2, this is equal to mod y1 minus z1. So this implies dxz plus dzy, this is equal to mod x1 plus mod z1 plus mod x2 minus z2 plus mod y1 minus z1. Now this is greater than equal to mod x1 plus mod y1 plus modulus x2 minus z2. Again, by triangles inequality, these two terms can be written as greater than equal to, sorry, this is z2. Mhm. Okay, I wrote this because mod y1, this is equal to mod y1 plus z1 minus z1. Just introduced plus minus z1. Now by triangles inequality, this is less than equal to mod y1 minus z1 plus mod z1. So these two terms turns out to be greater than equal to mod y1. Now this is equal to mod x1 plus mod y1. Yeah, this is what we hmm. y1 plus mod x2 minus y2. Why? Because yeah, z2 is equal to y2, and this is what we needed now. This is dxy. Therefore, dxy is less than equal to dxz plus dzy. Similarly, I would like you to try the third case where we have uh, x2 not equal to y2, and so that should be written as y2 not equals to x2, but this is equal to z2. The things will be exactly similar as in the subcase 2, just that we'll be replacing x by y. So I hope you can try this part. And if you have any doubt in whatever I did right now, if you find anything wrong, please let me know. Maybe I have done some mistake. Okay. If it's clear, then we can move ahead. Yeah, next one is easier. I would like you to think about it. So we have question 2. Let x be the set of real numbers. And for every xy in R, we define dxy to be equal to mod sine x minus y. So tell me whether this forms a matrix space or not. This is just one step solution. So since if I'm saying this is one step solution, that means clearly this is not a matrix space, because in order to prove that it is a matrix space, you'll need at least 4 steps. To try to see which property this is violating. Clearly this is positive, so first one holds. The problem occurs at the second one. No? Second one says that dxy is equal to 0 if and only if x is equal to y. Yeah, triangles inequality. Okay, so how? Can you give me, can you explain me how triangles inequality it is violating? Because I I didn't go to that. I got contradiction at the second step itself. So can you tell me how it is violating triangles inequality?
Yes, ma'am. Maybe we will be able to find such z such that d of xy will be 1 and that will be that should be less than equal to dxz plus sorry, yes, dxz plus
DZY,
dy.
something like this.
Yeah, so maybe we will find some z, I guess.
Yeah, you'll have to find. That's what I was asking now. So you can see that it is violating the second step itself. I You can try that triangles inequality also. I'll also see if I can find some example. So if I take x to be equal to 3 pi and y equals to pi, in that case, obviously x is not equal to y, but dxy, this is modulus of sine 3 pi minus pi is 2 pi and sine 2 pi is 0. So we are getting dxy to be equals to 0, but still x is not equal to y. So this is violating this condition. So you can also try to find some similar kind of examples where this is violating the triangles inequality. So therefore, this will not form a metric space. Is it clear? Okay, then let's move to next question. Consider the set X to be the set of rationals for any xy in X. We define dxy to be equal to mod x minus y. Now you can see, check yourself, check that this forms a metric. Check here we'll be checking whether the following sets are open or not. So we'll move ahead and see and look for the open sets. X minus y. Check whether the following sets are open in XD or not. So the first one is set of rationals and second one is so. So can you tell me whether Q is open in this matrix space or not? So can anyone of you tell me what do we mean by open set? Just your idea.
Ma'am, open set contains all the interior points,
All
all
of
its
its
interior points.
points, all of its points are interior points. Good.
Yes, ma'am.
So can you tell me whether the set of rationals will be open or not?
As we are subtracting the two rationals, we will get a rational, so it will be a point of rational. So I guess it should be open.
No, not in that way. Anyways, the matrix space itself is always open, no? The whole space X is equal to Q. The whole space is always open as well as closed. Any matrix space is open as well as closed in itself. Therefore, directly this space X is open. Since every space or we can write matrix space is open as well as closed. These are the trivial open closed sets, no? The whole space, the empty set closed in itself, then clearly Q is open in xt. So first one is open. What about second one? We have the set S, which includes elements of the type 1 by n. So if we see it on number line, this is 0, 1, 1 by 2, 1 by 3, and so on. Now suppose this set S is open. Suppose S is open in xt. This implies S naught, the set of all interior points of S, is equal to S. That means every point in S is an interior point. Now let S belonging to S be arbitrary. This implies there exists a neighborhood of S, some R positive, such that the ball around S of radius R, this is contained in S. Now if I take this S to be equal to 1, let S is equal to 1, this implies there exists some delta positive such that a ball, now this ball is in matrix D, ball around 1 of radius delta, this is contained in S. Now we'll use the density of rationals. This is 1, this is 1 by 2. Anything in between 1 by 2 and 1 is not in the set. But we know that there exist infinite number of rationals in between 1 by 2 and 1 by the density of rationals. So clearly, for any delta positive, there exists some q in set of rational numbers such that 1 by 2 is strictly less than r, strictly less than 1, and r greater than 1 by delta, 1 minus delta. So suppose delta is some distance from, this is 1 minus delta. Whatever small delta I take, I can still find a rational number in between. I hope this is clear. So this is 1 by 2, this is 1. So I'm taking delta. Whatever the delta is, we don't know the value of this delta. We know that just one such delta exists. Whatever small delta this is, I can find a rational number which is strictly greater than 1 and strictly less than 1 and greater than 1 minus delta as well. So that means this this q, sorry, this is q. This q does not belong to S, obviously, because this q is lying strictly in between 1 by 2 and 1, and q belongs to 1 minus delta to 1 plus delta. That is, which is a superset yeah, which is a superset of the ball around 1 of radius delta, because we are in the space of rationals. So anyways, this implies Q belongs to the set Q intersection. So we can write it better to be like this. Q intersection 1 minus delta to 1 plus delta minus S. Because Q is not in S, but Q is in this neighborhood intersection Q. But this is empty. Why? Because this ball is contained in S. Now this gives us a contradiction. Hence, S is not open in state. I hope this is clear. So the main idea was to use density theorem. If you have any doubt, please let me know. Okay. Let's move to next question then. Next, we'll be showing the taxicab metric. I hope you must have heard this name. Question 4. Show that in R2, the following known as the taxicab metric is indeed a metric. How is it defined? We define it as dxy, comma uv, where these are 2 points in R2. This is equal to mod u minus x plus mod v minus y. So we'll see that yes, this forms a metric and by satisfying the conditions. I think this was an exercise problem given in the lecture class. If you had tried, you can please let me know. Or else I'll do it. Clearly, since we are just adding up to modulus two positive terms, so this is always positive. Clearly, dxy uv. This is sum of two positive terms, so this is always positive. Next, we will see that dxy uv, this is equal to 0 if and only if, by definition, v minus y, this is equal to 0. Now, sum of two positive terms is 0 if and only if the two terms are 0 itself. And mod v minus y is equal to 0. And this happens if and only if u is equal to x and v is equal to y. That means both the components are equal. That means xy is equal to uv. So this condition also holds. Next is the symmetry, which is straightforward. because anyways we are working in modulus, so I can write it as mod x minus u plus mod y minus v, which is d of uv comma xy. So the symmetry also holds. Next is the triangles inequality. Is also quite straightforward only. dxy uv. This is equal to introducing plus minus. So we'll take another vector w comma z in R2 and introduce it in between. So this is u minus w plus w minus x plus v minus z plus z minus y. So by triangles inequality of the modulus, this is less than equal to mod u minus w plus mod w minus x plus v minus z plus z minus y. Now this is equal to this term u minus w and v minus z. This gives us d wz uv, and the other two terms gives us dxy wz. So that's what we need now. So this is the triangles inequality. Therefore, this XD is a metric space. So I hope this was clear. Okay. Next, we will see convergence. Convergence of sequences in metric space. Let X be any set with discrete metric. So can you tell me how this discrete metric was defined?
Yes, ma'am. D of xy equals to 0 if x equals to y, and 1 if x is not equal to y.
So when does a sequence converges in this discrete space? When does xn and x converges in x? So we have dxy, this is equal to 0 when x is equal to y, and this is 1 when x is not equal to y. So we need to see how is convergence, how can we look for convergence in the discrete space. So what do we mean by convergence? So if you can recall the epsilon definition, we say xn converges to x in any matrix space xd if for any epsilon positive there exists a stage n naught in n such that the distance between xn and x is strictly less than epsilon after this stage. So all the terms coming after xn naught, the terms are very close to x. That's how we define convergence. So now we need to see what happens in the case of discrete metric. Now this epsilon is arbitrary. This epsilon, I can take any epsilon. For this epsilon, I should be able to find some n naught. Now if I take epsilon to be if I take epsilon to be less than equal to 1. In that case, again, I should be able to find some n naught such that dxn x, this is strictly less than epsilon, less than equal to 1 for all n greater than equal to n naught. Now this d is the discrete metric, and discrete metric can have values either 0 or 1. In this case, they are saying that dxn is strictly less than 1. That means it should be 0. Otherwise, we don't have any other choice. Now, so this implies dxn x, this is strictly less than 1 for all n greater than equal to n naught, and hence dxn x is equal to 0 for every n greater than equal to n. Now this happens only if xn is equal to x for every n greater than equal to n. This suggests that after a stage, all the terms are equal. That means our sequence is something of the form eventually constant. So this implies xn is eventually constant sequence. Conversely, you can always see if a sequence is eventually constant, it will anyways converge. Therefore, in discrete matrix space, a sequence is convergent if and only if it is eventually constant sequence. This is a very good result. You should remember it. In discrete matrix space, a sequence is convergent if and only if it is eventually constant. So I hope this was clear. The definition of the metric, discrete metric, and how we define convergence in matrix space. Further, how it is affected by the discrete matrix space. Okay. Next, we will see convergence in the space of bounded functions. So, can anyone tell me how we define metric on the space of bounded functions? If you can recall the soup norm. Six. Suppose we consider the space. Consider x equal to the space of all bounded functions defined on a closed interval 0, 1, 0 to 1 to R with the soup norm metric. Soup norm metric is, write it as something d infinity f g. This is supremum mod f x minus g x, x belonging to closed interval 0 to 1. Again, we need to see the convergence in this space. When does a sequence Fn and x converges to some f in x? So again, we'll start by assuming that we have a convergent sequence and then look for its corresponding definition. Suppose Fn converges to f in x. t infinity with soup norm. Then for any epsilon positive, there exists some n naught in n, there exists a stage such that the distance between f and fn is strictly less than epsilon for all n greater than equal to n naught. Now this means, by definition, supremum mod fx minus fnx for all x in close interval 0 to 1. This is strictly less than epsilon for all n greater than equal to n. This implies for any x in closed interval 0 to 1, obviously mod fx minus fn x, this will be less than equal to the supremum. Because the element of a set is always less than equal to its supremum. X, this is less than epsilon for all n greater than equal to n naught. And clearly this n naught is independent of x. So this is suggesting us uniform convergence. We have mod fn x minus fx. This is strictly less than epsilon for all x in close 0 to 1 and for every n greater than equal to n naught. This is the definition of uniform convergence. That means Fn converges to F uniform. Conversely, also you can see that if a sequence is converging uniformly, it will converge in this space. Therefore, this is also a good result. Fn converges to F in this space of bounded functions with sup norm if and only if Fn converges to F uniformly. Similarly, try to see what happens for in the case of Cauchy sequences in the discrete space. Please tell me, how are Cauchy sequences seen? How can you see the Cauchy sequences in the space of in the discrete matrix space? I'll come back in 5 minutes. Please try to see how the Cauchy sequences look like in the discrete space. Yeah, Cauchy sequences are convergent. You're right. Further, Cauchy sequence need not be convergent always. Cauchy sequences are convergent in the space of real numbers when we have normal Euclidean metric. Otherwise, you cannot say. Convergent sequence is always Cauchy, not conversely. You will see further that there are spaces where Cauchy sequence need not be convergent. So please look how this happens in the case of discrete. In fact, we say, in the spaces where Cauchy implies convergent, those spaces are called complete spaces. Okay, I'll come in 5 minutes. Please try. I have question number 7. What are Cauchy sequences? Maybe taken epsilon less than 1, we will get this less than 1 for mn greater than n naught. Yeah, right. Eventually constant. So I think you got the idea. Exactly same the way we did for the convergent sequence in the discrete matrix space. Similarly, for epsilon less than 1, you'll get dxn xm to be equal to 0. So all the terms will be eventually constant. Good. Sequences in a discrete matrix space. Solution. Again, if xn is Cauchy, then for any epsilon positive, there exists a stage n naught such that dxn xn, this is strictly less than epsilon for all n greater than equal to n naught. And again, if we take epsilon to be less than equal to 1, in that case, dxn xm will be strictly less than 1 for all n and m greater than equal to n naught. This implies dxn xm, this is equal to 0 for all n m greater than equal to n naught. So that means after the stage n naught, all the terms are same. Hence, the sequence is again eventually constant. So what can we say about the completeness of discrete matrix space? Constant. We say a matrix space is complete if every Cauchy sequence is convergent. Now in the discrete matrix space, a Cauchy sequence is a eventually constant sequence, and eventually constant sequence we have seen earlier that obviously they're always convergent. Therefore, the discrete matrix space is always a complete matrix space, no matter what this space X is. Hence, if Xn is Cauchy, this implies it is eventually constant, and this implies this is convergent. Therefore, Cauchy in discrete matrix space, discrete matrix space, discrete matrix space. Therefore, discrete matrix space is complete. Is it clear? The completeness part? Okay, then let's move to next. Next, if you remember, we did some points at topology. Okay, let me write the question first. Question number 8. Let X be a matrix space. And S subset of X. Show that X, an element in X, is an adherent point and if and only if BXR, ball of radius R around X, intersection S is non-empty for each R positive, and that X is a limit point in this is X belonging to X, limit point if and only if BXR intersection S minus the set element X is non-empty for every R positive. So let's recall the definition of other endpoint. Recall let S be a subset of X. We say a point X naught, any point in X, need not necessarily be a point in S, is an adherent point of S if we can find a sequence Xn. Now this sequence is in S such that this Xn converges to X naught. And for the case of limit point, if we can find a sequence of distinct points, that this sequence is not a constant sequence, neither eventually constant sequence, all the terms should be different, distinct, and converging to X naught. In that case, we call that this point is the limit point. Further, if we can find a sequence Xn of distinct points, the terms in the sequence are distinct, such that again Xn converges to X naught, then this X naught is said to be a limit point of S. Now we need to show that X is an adherent point if and only if the set BXR, the ball around X of radius R intersection S, is non-empty for each R positive. So no matter what radius I take, if this is BXR, its intersection with S, so this is, if this is some S, this intersection should always be non-empty. So let's see how we can prove it. Solution. Let's start with firstly with the other endpoint case. And similarly, we'll see the limit point. Now suppose X naught belonging to X is an other endpoint of S. This implies there exists a sequence Xn in S such that this Xn converges to X naught. Now we need to show that B X naught R intersection S is non-empty for every R positive. Now, since this Xn converges to X naught, by definition of convergence, for any epsilon, instead of epsilon, I'm taking R positive. There exists a stage that obviously always depends on R, epsilon, such that the distance between Xn and X naught, this is strictly less than R for all n greater than equal to nr. That means this Xn belongs to the ball of around X naught of radius R for every n greater than equal to nr. And since Xn belongs to S for every n, this implies Xn belongs to Bx naught R intersection S for every n greater than equal to nr. Now, since this R positive was arbitrary, since for any R, I was able to find a lot of elements because after this stage nr, all the terms are in Bx naught R intersection S. That means for any R, we can find not just one, a lot of elements in this intersection Bx naught R intersection S. Therefore, since R positive is arbitrary, this implies Bx naught R intersection S is non-empty. X naught R intersection S is non-empty for every R positive. So I hope this part was clear. Conversely, let Bx naught R intersection S is non-empty for every R positive. And we need to show that this X naught is an other endpoint. That means endpoint, that is, there exists a sequence Xn in S such that Xn converges to X naught. Now, since Bx naught R intersection S is non-empty for any R positive, obviously this will be non-empty for R equals to 1. So I can find some element in Bx naught 1 intersection S. So I name this as X1. Now, since Bx naught R intersection S is non-empty for every R positive, this implies there exists some X1 belonging to Bx naught 1 intersection S. Similarly, there exists some X2 maybe equal to X1, maybe distinct. We don't care. We just need a sequence. The sequence need not be of distinct terms. So you can find this X2 in Bx naught 1 by 2 intersection S, and so on. We have Xn in B X naught 1 by n intersection S. Now I claim that this sequence Xn will converge to X naught. This implies from here, this implies dx x naught, this is strictly less than 1. From here, sorry, this is x1. dx2 x naught is less than 1 by 2. From here, we have dxn x naught, this is strictly less than 1 by n. Therefore, dxn x naught strictly less than 1 by n for every n in n. Now, for any epsilon positive, clearly by using the Archimedean property, the way we prove the sequence 1 by n converges to 0, let epsilon positive be arbitrary. This implies by Archimedean property, there exists some n epsilon in n such that dxn x naught strictly less than 1 by n is strictly less than epsilon for all n greater than equal to n epsilon. That is, the sequence xn converges to x naught, and hence now since the sequence xn was in S, all the terms were taken from the set S, which converges to x naught. Therefore, the point x naught is an adherent point of S. Therefore, x naught is an adherent point of S. I hope this was clear. Next, we will see what happens for the case of limit point. Just get here. Next part is the case of limit point. Now let x naught be a limit point of S. Says x naught is an element in X. Be a limit point of S. We need to show that Bx naught R intersection S minus x naught, this is non-empty for every R positive. Now, since x naught is a limit point of S, we can, by the definition of limit point, by definition, we can find a sequence xn in S with distinct points, distinct terms, such that the sequence xn converges to x naught. Clearly, xn, yeah, by distinct terms, we means that xn is not equal to x naught for every n and n. Yeah, because if some terms were equal to the limit, so it would directly imply that the sequence was eventually constant. But since the sequence has distinct term, so we can see that the sequence came through was never equal to x naught, the term. This implies, again by definition of convergence, instead of epsilon, we'll be taking R. This implies for any R positive, there exists a stage in R in N such that the distance between xn and x naught is strictly less than R for all n greater than equal to n. This implies xn belongs to the ball around x naught with radius R, and since xn is an element in S, so I can take it intersection S. Moreover, since xn is never equal to x naught, I can remove this set x naught for every n greater than equal to nr. That means bx naught r intersection S minus the set singleton set x naught is non-empty. And since R positive is arbitrary, we have Px naught R intersection S minus x naught. This is non-empty for every R. That's what we needed. Conversely, conversely, suppose this Bx naught R intersection S minus x naught is non-empty for every R positive. Again, we'll, as done earlier, we'll construct a sequence by picking up terms from these non-empty sets. Let x1 belongs to bx naught 1 intersection S minus x naught. x2 belongs to the same with just 2. So let me write it. xn for every n in n. This implies dxn my x naught, this is strictly less than 1 by n for every n in n. Now this says that xn converges to x naught as n tends to infinity. Again, as done in the case of the other endpoint, how using the Archimedean property. Now, next step is to show that this sequence should be of distinct terms. So if, yeah, because all the terms, none of the term was equal to x naught, and the sequence was converging to x naught. So even if some terms were same, we can remove those terms from the sequence, and the leftover sequence, the one having distinct elements, will also converge to x naught. So that corresponding that sequence with distinct terms will be taking, and hence we'll get that x naught is a limit point. Let's see. Now, since xn belongs to bx naught 1 by n intersection S minus x naught for every n in n, and xn converges to x naught, which is not equal to xn for every n in n, because all the terms are taken from this set. This implies even if the terms, even if some terms were same, we can remove them. And still the sequence will converge to x naught, thus taking that sequence, thus taking that sequence xn of distinct terms in S, we get Xn converges to X naught. Therefore, X naught is a limit point of S. Hence, X naught is a limit point if and only if the set Bx naught R intersection S minus the singleton set X naught is non-empty for every R positive. I hope this is clear. If you have any doubt, you can ask. Okay. Okay, then let's move to next question. Question 9. Show that if V is a normed vector space, I hope you all remember what do we mean by normed vector space. So a vector space that has a norm as well, norm having three properties. Show that if V is a normed vector space, then the function dVw defined as equal to norm of V minus W for every V and W in V is a metric on V. So eventually we will see that a norm space has a metric. So every norm space is a metric space. So again, we'll have to check the properties of the metric, those four properties. Clearly, by the property of norm, we know that this norm is always positive. Next comes dVw is equal to 0. Now this is equal to 0 if and only if norm V minus W is equal to 0. And then by the property of norm, this is equal to 0 if and only if V minus W is equal to 0. That means V is equal to W. Next is the symmetry property. dVw, this is again by symmetry of norm. Next is the triangles inequality that comes by the triangles inequality property of norm. For any U, V and W in V, we have duv. This is equal to norm U minus V, which is norm U minus W plus W minus V. Then by triangles inequality, U minus W plus W minus V, which is duw plus dwv. It was quite straightforward. Therefore, this forms a metric on the space V, and hence every norm space, normed vector space, vector space is a matrix space. I hope this was clear. This was very trivial enough. Next, we'll see a problem related to the inner product. I hope you remember the properties of inner product. Okay, let me state it. 10. Show that the inner product of any vector with 0 is always 0. Let's just recall the properties of inner product. So a function written in this way from V cross V to R is said to be an inner product if it satisfies the following. Number one, the inner product with itself is always positive, and this is equal to 0 if and only if V is equal to 0. Next, we have again symmetry. And the third one is linear transform. So the map for fixed, so we say that this is linear component wise. So if we fix the second component, it is a linear transformation with respect to the first component. It's a linear transformation. So using these properties of inner product, we will see that for any vector v in the inner product space v, its inner product with 0 is always 0. V comma 0, this is equal to, by symmetry property, I can write it as 0 comma v. Now this v, this 0 can be written as w minus w, because 0 is the 0 vector. In a vector space, we know that we can write 0 to be equal to difference of a vector from itself. So now we use the third property of the inner product, the linearity with respect to the first component. So this is equal to w comma v plus minus w comma v. Again, by linearity, I can take this minus outside. So this is 0, subtracting the same terms. So anyways, this might seem trivial, but in this way, you understand how we are using the definition. So at each step, this is by linearity with respect to, or we can just say the third property of the inner product. Right. Now, since this v was arbitrary, I can write it as anyway. Okay, next we will see the open set in the subspace matrix. Question number 11. prove that G is open in Y, which is a subset of X. So now we'll see how the restriction of metric is used to define to define metric on a subspace. That's what we call submetric. If and only if we can find an open set U such that G is equal to Y intersection U. Now, by in open set, we mean open in X. Solution. Let Y be subset of X. Then we have dy. The if D was the metric on X, dy is the restriction of D on Y. That's how we define a metric in on the subset. So dy be its corresponding metric. Suppose G is open in Y. G is open in Y. That means its every point is an interior point. This implies for any x in G, there exists some Rx positive such that x belongs to the ball in Y around x with radius Rx, which is contained in G. So that's how we define the open set. That means X belongs to the set of all those points Y and Y such that the distance between X and Y is strictly less than Rx. This is contained in G. So this is the definition of the open ball. Now this implies clearly this X is in Y and X from here I so this is dy. X belongs to Y and Y such that and this is by definition I can write this dy to be equal to D. That was the metric on X. So this is a subset of all those Y in X such that dxy is strictly less than Rx. So this is an open ball in X around X with radius Rx. So this means X belongs to Y intersection dx x Rx for any X in G. This X element in G was arbitrary. So this implies I can write G is contained in Y intersection union X in G Bx x Rx. Now this is an arbitrary union of open balls. We know that arbitrary union of open balls is an open set. I can write it as Y intersection U, where this U is an arbitrary union of open balls in X. So this is open in x. So therefore, we have G contained in Y intersection U. Now, let x naught belongs to Y, sorry, this is intersection, Y intersection U. This implies x naught belongs to Y and x naught belongs to U, which is equal to union x in G bx x r x. This implies x naught belongs to bx x r x for some x in G. This implies distance between x naught and x is strictly less than Rx. And this is in terms of x. Therefore, we have x naught belongs to y and the distance between x naught and x is strictly less than Rx. Now, since x naught is in y, yeah, from here x naught is in y, this x is in G, which is in y. Therefore, this dx, we can write dy x naught x is equal to dx x naught x. This is strictly less than Rx. Why? Because x naught is in y and x is in G, which is again a subset of y. This implies x naught belongs to ball in y at x, sorry, around x with radius Rx. Now we know that this is contained in G from here. This is contained in G. This implies x naught belonging to G. We took x naught in Y intersection U and proved that x naught is in G. This implies Y intersection U is contained in G, and hence from star and hash get G is equal to Y intersection U, where this U is an open set in X. So therefore, any open set, whenever G is an open set in Y, it can be written as Y intersection U for some open set U in X. So conversely, next we need to show that any set which can be written as written in the form of Y intersection U is open in Y. Conversely, let G is equal to Y intersection U for some open set U in X. We need to show that this G is open in Y. In Y. Okay. So in order to show that it is open in Y, we will show that every point is an interior point with respect to the matrix in Y. Obviously, clearly this is a subset of Y. Now let X belongs to Y intersection U. This implies X belongs to Y and X belongs to U. Now, since U is open in X, since U is open in X, This implies there exists some Rx positive such that X belongs to the ball in X around X with radius Rx, which is contained in U. That's the definition of open set. Now consider the ball. Consider the ball in Y around X with radius Rx. This is the set of all those points Y in Y such that dy yx, obviously x is in Y, so we can talk about dy yx. This is strictly less than Rx. Now this is equal to Y in Y dyx, or you can write it as dx. It's up to you. You can always omit this x. I'm writing it to specify everything. This is strictly less than Rx. That's how we define metric in the subspace. Now this is a subset of all those y in x, because obviously y is a subset of x. Dx yx less than Rx. Now this is equal to bx x Rx, which is contained in U. Why? Of this by equation first. So from here we get by xrx is contained in U. Also clearly this is a subset of Y, so I can write it as U intersection Y. Therefore x belonging to B y x r x is contained in Y intersection U, which is equal to G. Since x belonging to G, we started with some x in G is arbitrary. Since x belonging to G is arbitrary, this implies G is open in Y. I hope this is clear. Okay, I'll stop here because otherwise I won't be able to finish next question. If you have any doubt and if you want something specific to be discussed in next class, so that I prepare accordingly, or else I'll do the in between exercise questions. Which lecture? The one I'm taking right now? I'll upload it on YouTube. You can watch it over there. Okay then. And yes, do you want something specific to be discussed in next class? If you have some doubt related to theory class, some topic that you were not able to understand. This was new to me, so I will have more doubts in next class to be discussed. Okay, in next class you can tell me. So if I'm able to tell you that right at that moment, I'll explain, or else in next class I'll prepare accordingly. Okay then, thank you. We'll meet next Sunday. Okay.